Alright, so our topic for today is all about equation of the line and equation of the plane. So first we will discuss equation of the line. So as we can see, we know that a line, so let's have first in R2. So a line, let's have this. So let's have L. Alright, so the definition of a line in Cartesian plane or a line is determined by a point that lies on it, so we call it P0, and the vector that is parallel to the line. So we call this vector V. V, so V with the arrow above. So we have this A comma B. Now let us define the equation of the line. So let us have this fixed point P lies also in the line. So let's have some notations. So P sub 0 can be also written as x0, y0 and P be xy. So if we, from this figure, we know that P, P0, so if we take the distance of this, it is equal to um, V times a constant T, where T be element of R. So by this, um, we have x minus x0, comma y minus y0. And then we have t multiplied by the vector a comma b. Now, um, this difference here, so I'll decompose this. So we get x comma y minus x naught comma y naught. So that is equal to, so I will multiply this t to this vector. So we get TA, TB, and then um, we can isolate or we can transfer this x naught y naught vector here to the right side of the equation. So we will get x comma y equals, so the vector x0 y0 plus the vector ta t, and then we add these two vectors, so that yields x0 plus ea comma y0 plus e. b. Hence, so we will get x. So let's have x of t. We have x0 plus at and y of t be y naught plus bt. So this system of equation is the parametric equation of the line L. Alright, so we are done with equation of the line. So let's have equation of the plane. So let us draw a three-dimensional space. So we have x, y, and z. And let us draw a plane here. Now, the definition of a plane is that a plane is determined by a normal vector. So we call it n with an arrow on the top and a point that lies in the plane. Now, if we have an arbitrary point P, so let us connect it. So we have this 90-degree angle. So based on the figure, if we take P, my P0, the distance of it, so we have this x minus x naught, y minus y naught, and z minus z naught. And then for the normal vector n, so we have the so any arbitrary constant, so a, b, c. Now, in the figure, um, it has a 90-degree angle on it. That means if we take the dot product of these two vectors, it would be 0. So the result would be 0. So by this we manipulate or derive. So P naught. So we have this. So dot product with the vector ABC. So equate to 0. So we will have A multiplied by x minus x naught plus B multiplied by y minus y naught. And lastly, we have C multiplied by z minus z naught. And then we equate it to 0. So this equation is the equation of the plane. So let's have cylindrical coordinates. So let us draw again the three-dimensional space. So we have x, y, and z. So suppose we have a point here. So we have P. Now in cylindrical coordinates, so we draw a cylinder like this. So we have here the radius r, the angle theta, so the rotation is here. Okay, so this is the figure of cylindrical coordinates. So cylindrical coordinates, by its word cylindrical, so it's like a cylinder. So here's the point: x0, y0, z0. Now for the parameters, so r must be greater than or equal to 0. Theta is between 0 to 2 pi. So the rotation, so we have from x, so we have in this direction. Now to transform the point x naught, y naught, z naught in cylindrical coordinates, so we have this coordinates. So we have r cosine theta, r sine theta, and z naught. So meaning if you have a radius r and an angle theta, so you rotate first the angle and then find uh, the coordinate in the z-axis. Now to obtain r for the formulas, we have square root of x squared plus y squared, and for the theta, we can use this formula. So tangent theta equal to y over x. For the spherical coordinates, so we have spherical coordinate. So let us draw again a three-dimensional space. So for example, we have this point E. So to obtain, uh, so we have x0, y0, z0. So we have, um, let us first draw a line here, and then have, uh, a line here, and a line in here. And then for the rotation, So we have this angle, theta. We also have this rotation, so we call it phi, and the radius, rho. So in spherical coordinates, we have three parameters. We have the theta, rho, and phi. So it's something like this. Let us draw here. So the rotation, and then you also have this rotation, something like a half sphere. So let us now draw um, the parameters. So the domain of the parameters, we have theta. Theta is between 0 to 2 pi. Phi is between 0 to pi. R greater than or equal to 0. So in the figure, this is R, and then rho is also greater than or equal to 0. So to obtain rho, we can use the formula rho equals x squared plus y squared plus z squared. To obtain the angle theta, we can use the formula tangent theta equal to y over x. And for phi, we can use the formula cosine phi equal to z over